Okay, in this video, we're going to look at some applications of the gradient vector operator. So in particular, we're going to consider a two-dimensional surface defined by the scalar equation z equals x squared minus y squared plus 5xy plus 2x plus 4. Just briefly, when you got z equals to a function like this, where the x and y occur in quadratic manner, these two terms determine the shape of the surface. So if x and y x squared and y squared have got opposite signs, then you've got what is called a hyperbolic paraboloid. Hyperbolic paraboloid is going to be shaped something like this, where this is also going to have something like that shape. Okay, here we want to find the directional derivative of this function at 2 minus 1 1. So that's basically going to be the slope of this surface at this point along the direction of this vector here, and then want to find the direction along which the slope of the surface is maximum at that point. So as you might imagine, if you're on this surface at some point here, if I can choose say this point here, then if you're going in this direction, the slope is going to be 0. If you're going in that direction, you're going down, so the slope is going to be negative. If you're going in that direction, it's going to be positive, but you expect the slope along this direction to be maximum positive, along that direction to be maximum negative. So here we want to find direction along which the slope is maximum at this point, and then want to find the value of that maximum slope at that point. Then finally, we're going to find the equation of the tangential plane at the same point. So tangential plane is a bit like tangent in 2D, so that's going to be your tangent. But if you are in 3D, then this is actually going to be a plane, so something like that, and then it touches your surface at only one point. So okay, let's get on with the first one. So we need to find the directional derivative. So the formula for the directional derivative along the direction A hat of phi is given by the gradient of scalar function phi times the unit vector, and then this is going to be evaluated at that particular point, in which case our point is this one here. So first of all, let's talk about phi. To get phi, typically you want to express your equation in terms of bringing everything to one side. So we want it to be something equal to 0. So that means for our case, phi is going to be, if you bring everything to the side where z is, so it's going to be z minus x squared plus y squared minus 5xy minus 2x minus 4. Then the gradient of this, so the x component is simply going to be the derivative of this with respect to x. It's going to be minus 2x from this term, and then minus 5y, and then minus 2 from this term. The y derivative is going to be 2y minus 5x, because these are the two terms involving y. Then the z derivative is going to be 1. Then we want to evaluate this at the particular given point, which is 2 minus 1, 1. So if you plug in x is 2, y is minus 1, and z is 1, then this component is going to give us negative 4. It's going to be 5, so that's 5 minus 4, which is 1, and then minus 2, so that's going to give us negative 1. Just make sure this is correct. Yeah, so x is 2, so that's going to be negative 4. Y is negative 1, so it's 5 minus 4, which is 1, and then take away 2. 1 take away 2, so that's got to be negative 1. Then here, if we plug in y is negative 1, that's got to be minus 2. And then x is 2, it's going to be minus 10. So this is going to be minus 12. And then the last one is a constant, so it's just going to be equal to 1. So that's going to be the gradient vector at the point 2, negative 1, 1. Then next we need the unit vector along the given direction. So if we take this and call it vector A, we need the unit vector along the direction of A. So it's just going to be that vector, which is 2 minus 7, 1. So the unit vector is going to be the vector A divided by the magnitude of the vector A. So we said it's 2 minus 7, 1. So this is going to be divided by the square root of 2 squared plus 7 squared. So that's going to be square root 54. 2 minus 7, 1, square root 54. So that's going to be the unit vector along the direction of this given vector A. And so the directional derivative which is required is going to be negative 1, negative 12, 1 dot 2, negative 7, 1 divided by square root 54. So in the first instance, going to have minus 2, and then 7 times 12 is going to be 84, and then 1 times 1 is 1 divided by square root 54. So it's going to be 85 minus 2, it's going to be 83 over square root 54. So that completes our part A. And then in part B, we're looking for the direction along which the slope of this hyperbolic paraboloid is maximum at this point here. And from the theory of the gradient, that is always going to be along the direction of the gradient function. So so all we can do here is write slope. Okay, so we're saying here the maximum slope is always along the direction of grad. So this is always along the direction of the gradient of phi. So that means in this case it's along the direction of this vector here, which is minus 1, minus 12, 1. So that answers the first question. What is going to be the magnitude of the slope? That is always going to be given simply by the magnitude of the gradient vector. So minus 1 minus 12, 1. So this is going to be 1 plus 144 plus 1. This is going to square root 146. So that's going to be the slope. In fact, if you check, you should, we will find that this slope here is smaller than the slope here. Let me just do it numerically. So numerically, square root 146 is around 12.08, whereas 83 divided by square root 54 is this one is 11.29, which, as you can see, is smaller than this. So if you are at the point negative 2, 1, 1, negative 2, negative 1, 1, then the maximum slope of the surface at that point is going to be along this direction. The slope is going to be given with square root 146. Okay, then finally, find the equation of the tangential plane at that same point. Now, so when it comes to the tangential plane, if you imagine this is our surface, then and this is our point in question, the gradient vector is always going to be at 90 degrees. So that means if this is our tangential vector, then the gradient vector is going to be a normal vector to the tangential plane. Okay, our point is 2, negative 1, 1. The gradient vector, which is going to be the normal vector, is minus 1, minus 12, 1. Minus 1, minus 12, 1. So this is going to be our normal vector of the tangential plane. Now, from the theory of planes in 3D, then the equation of the plane is going to be equal to the normal vector dot the position vector of a point x, y, z minus the position vector of a given point on the plane. Now, in our case, R0 is going to be the position vector of this point here, 2 minus 1, 1. Of course, this just x, y, z. So when we plug this in, the normal vector is minus 1, minus 12, 1. Then dot is going to be x minus 2, this 2. It's going to be y plus 1, this 1. It's going to be z minus 1. This must be equal to 0 because these two are always going to be perpendicular to each other. So what this is going to give us is 2 minus x minus 12 into y plus 1, and then plus z minus 1 equal to 0. Then all we're going to do is to bring all the constants to the right hand side. So the variables, we're going to have z here, then we're going to have minus x from here, then minus 12y. Then on the right hand side we're going to have 1, then we're going to have 12, minus 2. So it's going to be z minus x minus 12y. This is going to be 13 minus 2. So that is going to be the equation of the tangential plane of this hyperbolic paraboloid at 2 minus 1, 1. Right, at this point we're going to give you a chance to have a go at a similar question. We'll actually do exactly the same question. We'll just alter the equations. Okay, so in for your question, you're going to do work with the scalar equation 7 minus x squared minus y squared plus x minus 5y. One moment. Yes, minus 5y. Okay, so in this case, since the signs of x and x squared and y squared are the same, then this equation is called a paraboloid of revolution. So this is a paraboloid of revolution. In terms of its shape, it's going to be shaped something like that. So basically, if you just take a parabola and rotate it about its axis, then you get a paraboloid of revolution. Okay, you are going to be finding the directional derivative at 1 minus 1, 11, along the direction of the vector 4i minus 2i minus k. Then the same question here, we're going to have 1 minus 1, 11, and same thing there, 1 minus 1, 11. Okay, so if you'd like to have a go at that, you can just pause the video, and then when you are done, then you can press play, and then it's going to enable you to compare your answer with our solution. All right, we're now going to scroll down to our solutions for the questions of the question of the problems with the details in pink here. We would like to implore you, of course, to subscribe to our channel to support the work we do, and like the video. Okay, so in this case, our phi is going to look something like this. If we bring everything to the one side, then this is going to be the gradient. So the x derivative to x minus 1, y derivative to y is 5, z derivative is 1, is the partial derivatives. Then if we plug this, we get 1, 3, 1. And then the unit vector along the direction given is going to be given by this. This is the vector given, which is divided by its magnitude. And so doing the dot product of the two gives us that the directional derivative is minus 3 over square root 21. That means the slope along this given direction is actually negative. Then the maximum slope is along the direction of the gradient, and that is going to be given by this, which is the magnitude of this vector. And then for the tangential plane, the gradient vector is going to be our normal, and then if we plug into that standard equation, that gives us that equation there. Thank you.